In this video, we're going to look at a geometric problem, and again, how optimization can help us work with it. We're going to imagine our usual x, y, and z axes and a plane that lives in 3 dimensions. Now, what we can do is try to sketch that, or we can just imagine it as some plane like this. What we're looking for is the point on the plane, so out of all the points on the plane that we've drawn, which is closest to the origin. So we'll have our origin here, and we can imagine that there's some point that will be closest on the plane versus, say, another point over here. This will be further. There's going to be one point that's closest. We'll then use the second derivative test to confirm that what we found is actually a local minimum for the distance. But just from this sketch, we expect there's going to be one single critical point, and it's going to be a local minimum. Now, this is a classic word problem where we have to define the function ourselves. So what do we want to optimize? We want to optimize the distance from some point. Well, we don't know what the point is. Let's give it x, y, and z coordinates. Some point on the plane to the point 0, 0, 0, the origin. Well, we have a lovely formula for that, which is square root of x minus 0 squared plus y minus 0 squared plus z minus 0 squared. Or, of course, tidying that up, square root of x squared plus y squared plus z squared. So what we'd like to do is optimize this, take its derivatives, set them equal to 0, and so on. However, we can see immediately there's going to be some messy stuff happening because of the square root. If we take a derivative of this, we're going to have chain rule stuff all over the place. What we'd like to do is work with something a little bit simpler. And we can do that looking at the distance squared. We've saw this in earlier videos in single variable optimization. If we're trying to optimize the minimum distance, and say the distance was 4, then if we optimize or try to minimize the distance squared, we're going to find exactly the same location. The smallest distance is also going to correspond to the smallest squared distance, and the perk is we don't have this nasty square root to deal with as we're doing our derivative calculations. So that's what we're going to work with in this problem because of that simplification. There's no problem working with this one here. It just ends up with more complicated looking derivatives, but giving us the same answer in the end. So we're going to focus on this, look for minima, but also taking into account the fact that we're working with a plane to help us narrow down our selections of x, y, and z. So we have our function, let's call it f, and it is x squared plus y squared plus z squared. But we can't just pick any x, y, and z. We have to pick one from the plane. What that means is we have to use this somehow to simplify our choices. And I think the easiest one to focus on here is the y because it has just a 1 coefficient. We can easily re-express this as y is 2 minus 2x minus 5x, bringing these terms to the other side. And that says once we pick x and z, we can't pick y any way we like. We have to pick it according to this formula. So we will combine these two ingredients here, and we'll get x squared plus, we might need some more room here, y squared, but that's 2 minus 2x minus 5z all squared. That's our y squared term. And z squared can stay the same way. And that gives us a function of 2 variables that we can then differentiate and work with. Except we note that it's not a function of x and y. It's a function of x and the other variable we kept, which was z. All right, our next step is to find the critical points. We're going to take the derivative of that function with respect to x. That'll give us 2x. We'll have to take the derivative of this, which will be 2 times everything inside, and then times the derivative of the inside with respect to x, which is -2, and plus nothing. The y derivative, except we don't have y's, is the z derivative. We fall into some patterns. We have the z derivative of x squared is 0. Same idea for this mixed term. we get that to the power 1 times the z derivative of the inside, which is negative 5, and then plus 2z's. And because we're looking for critical points, we're going to set both of those equal to 0. We're looking for the points where the derivatives are 0. Now we're faced with the challenge of solving those two equations for x and z. I think it makes the most sense to expand all of this out as much as possible. We're going to have 2x, and then we have 2 times negative 2, so that's 4 times everything inside. Negative 4 times everything inside. So we'll have negative 8 plus 8x plus 20z's equals 0. And in the expression down here, we'll put the 2z's first, this one, and then we're multiplying by negative 10 for everything inside. So we will have negative 20. 10 times that will be positive 20 x's. 10 times that will be 50 z's equals 0. We can tidy those up a little bit further. We'll have here, well, actually we can divide through all the way through by 2. So let's call this equation 1 and 2. And if we simplify them and collapse the like terms, we actually have 10x's here. If we divide through by 2, we'll have 5x's. So we'll have 5x's, divide through by 2 is 10z's, and divide through by 2 for the 8 will be 4. Similar thing here. The z's, we have 52z's. If we divide through by 2, which we can, we'll have 26z's. Divide through by 2, we'll have minus 10. And divide through by 2 for the x's, we will have 10x's. And in fact, this expression we can divide through again by 2 and actually have 5x plus 13z minus 5 equals 0. The reason to simplify is simply to have less to worry about as we're going through the solving process. The additional perk of this is that we can actually take this equation, called 3, and this equation 4, and subtract them, because that'll get rid of our x values. Take this entire expression here, subtract this entire expression here, and we will end up with negative 3z's. Minus 4 plus 5 is plus 1 equals 0, and out comes z equals 1/3. That's not bad, given how complicated those original expressions were. Once we have z, we can sub that into any of the other equations we had. Let's put it into 3, because it has nicer numbers in it. Sub that into 3. We get 5x's plus 10 times 1/3 minus 4 equals 0. X is going to be 1/5 times positive 4 minus 10/3. And if we get our fraction calculator out on that, we end up with 2/15. And so we end up with a single critical point at x equals 2/15 and z equals 1/3. And if we wanted to, we could add the third coordinate, our y coordinate from up here, 2 minus 2x minus 5z's. Using these values, we get 1/15 for y. That would be a point on the plane, sketched out loosely here, which would be closest, we think, to the origin. We're going to confirm that with the second derivative test. For that, though, we're going to need our first derivatives already computed on the next page. For the second derivative test, we take the additional derivative of each of these. Fortunately, because things were quadratic earlier, this turns out to be not too bad. We're going to end up with 2. We do have to differentiate this, but we have a minus 4 multiplier overall. And then we take the derivative of the inside with respect to x. We're going to have another negative 2. Again, careful with your variables. This time z is the second variable. Same idea. We're going to have a 2. And then we're going to have negative 10 times the interior here, which is negative 5 when we take the z derivative. Then we have, last but not least, the mixed derivative xz. We take the z derivative of this expression, we get 0. We have the minus 4, 2, and minus 2's, and then times the derivative inside with respect to z. That will be positive 20. Since these are all numeric values, we may as well tidy that up. This will be 8 plus 2, which is 10. This will be 50 plus 2, which is 52. And notice here, we have a nice simple second derivatives everywhere. We don't even need the value. The curvature is always the same at every location. So our d is going to be 10 times 52 minus 20 squared. And that's going to be 520 minus 400, or 120. The value being 120 is not so critical. It's that it's positive that matters, because that indicates as a product of concavities that the concavities are the same. And then we look at any one of these, say the xx derivative is positive as well, which means concave up. So the scenario we're looking at here for our function is that we have a critical point, tangent plane flat, but it's concave up around there. So what we found, which was x equals, last page, 2/15, a third, and 1/15. We'll put them in the order we usually put our coordinates in. And we have our 1/3 is a local minimum for the distance. The point we found is in fact closest to the origin, which is what we expected given the diagram we drew initially.